Hey guys, today we're going to be going over empirical and molecular formulas. So our empirical formula, remember that's our smallest whole number ratio of our atoms within a compound. And then our molecular formula is our normal formula that we would find that contains all of the atoms associated with that structure. So let's start with this problem right here. We have a compound. It was analyzed to find and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.6755 grams of hydrogen. We see each one of these have 3 significant figures, so keep that in mind when we're doing this. So what we're going to do is we're going to go from grams and then into moles, and then we're going to use the one that produces the smallest amount of moles and use that to figure out our mole-to-mole ratio. So let's start by converting from grams to moles using our molar mass. So we have 13.5 grams of calcium. For every 1 mole of calcium atoms, we have a mass of 40.078 grams. So we'll divide our 13.5 by 40.078, and what we get is 0.337 moles of calcium. And then we'll do the same thing for our oxygen, 10.8 grams of oxygen, 1 mole of oxygen, and this is atomic oxygen, not molecular oxygen, so it's not O2. Keep that in mind. So we're going to use what's exactly on the periodic table, our 15.999. That's how many grams are in 1 mole of oxygen atoms. So we take our 10.8, divide by 15.999, giving us 0.675 moles of oxygen. And then we're going to go from our grams of hydrogen, 0.675 grams of hydrogen. Again, this is atomic hydrogen, so 1 mole of hydrogen atoms has a mass of 1.008 grams. So we'll take our 0.675 divided by 1.008, and we get 0.667 moles of hydrogen. Now, we're going to take our smallest number, our calcium, and divide all the rest of them by that value. So we're going to divide by 0.337. And we get 1 here. We get 2 here and 2 here. So this gives us an empirical formula of CaO2H2. Now, more than likely, since we're talking about ionic structure here, we are probably talking about calcium hydroxide, this right here. And calcium is an alkaline earth metal, which is a 2+. Hydroxide is a 1-. So this empirical formula makes sense. Okay. Let's look at our next question. L-DOPA, this is a drug used for the treatment of Parkinson's disease, is 54.82% carbon, 5.62% hydrogen, 7.10% nitrogen, and 32.46% oxygen by mass. We want to use this information to determine our empirical formula of L-DOPA. As a note, these are percentages by mass. It does not matter the mass we decide that that's a percentage of. So I usually just assume in these type of situations where I'm given percent by mass that I have a total mass of 100 grams. So my total mass here is going to be 100 grams. So I'm going to take and basically multiply by the fractional percentage or fractional amount. So this would be 0.5482. This would be 0.0562. This would be 0.0710. And this would be 0.3246 in a fraction. So if we're using a fractional amount, so I'm going to take my 100 grams and multiply it. And we're just going to assume that this is an infinite significant figures because it's exactly 100 grams. We'll multiply it by our 0.5482, and we get 54.82 grams, which should make sense. We've taken a percentage, we've divided it by 100 to get a fraction, and then we've multiplied it by 100 to get back to grams. So each one of these are just going to be the gram amounts of those percentages. So we'll have 54.82 grams of carbon, 5.62 grams of hydrogen, 7.10 grams of nitrogen, and 32.46 grams of oxygen. I just wanted to kind of go through that to see, so you guys would see what or where I got these numbers from. Okay, now I'm going to use my molar mass to go from grams of each of my elements into moles of each. So carbon, 1 mole of carbon has a molar mass of 12.011 grams. So when I take my 54.82, divide it by 12.011, I get 4.564. We have 4 sig figs here, moles of carbon. Then I'm going to take my hydrogen. 1 mole of atomic hydrogen has a mass of 1.008 grams. So 5.62 divided by 1.008, giving me a value of 5.58 moles of hydrogen. This 3 sig figs starting out, we end up with 3 sig figs at the end. Then we'll take our nitrogen. 1 mole of atomic nitrogen has a mass of 14.007 grams. So we'll take our 7.1, divide it by 14.007, giving us 0.507 moles of nitrogen. Again, 3 significant figures. And then our oxygen, 1 mole of atomic oxygen is equal to 15.99 grams. 999 grams. So 32.46 divided by 15.999 gives us 2.028 moles of our oxygen. And now we can divide by our smallest number, which is nitrogen. So we'll take and divide by 0.507. And we get a 1 here. When we take 4.564 divided by 0.507, we get 9, or approximately 9. We take 5.58 divided by 0.507, we get approximately 11. And then we take 2.028 divided by 0.507, we get exactly 4. Interesting. So we would say that our formula here is C9H11NO4. So that is our empirical formula for L-DOPA. Okay. Now let's try and take this idea, take this idea and go from an empirical formula into a molecular formula. So once we know our empirical formula, if we know our molar mass, we can figure out what our molecular formula is. So first we have to figure out what our empirical formula is, and then using the mass of that empirical formula and the molecular formula's mass, the molar mass of the molecule, we can figure out what our molecular formula is. So let's take NutraSweet. It has 57.14% carbon, 6.16% hydrogen, 9.52% nitrogen, and 27.18% oxygen. Again, I'm just going to convert these directly into grams. So I have 57.14 grams of carbon, 6.16 grams of hydrogen, 9.52 grams of nitrogen, and 27.18 grams of oxygen. So convert each of these into moles. So 1 mole of atomic carbon is 12.011 grams. So taking our 57.14 divided by 12.011 gives me 4.757 moles of carbon. And 1 mole of atomic hydrogen is equal to 1.008. 1.008 grams of hydrogen. We take our 6.16 divided by 1.008, giving us 6.11 moles of hydrogen. And then our nitrogen, 1 mole of atomic nitrogen, 14.007 grams. 9.52 divided by 14.007 gives us 0.680 moles of nitrogen after we round. And then oxygen, 1 mole of atomic oxygen has a molar mass of 15.999 grams, so 27.18 divided by 15.999 gives us 1.699 moles of oxygen. Our smallest mole here again is nitrogen, so we'll divide everything by our number of moles of nitrogen, 0.680. When we take 4.757 divided by 0.680, we get approximately 7. And when we take 6.11 divided by 0.680, we get approximately 9. When we take 0.680 divided by 0.680, we get 1. And then when we take 1.699 divided by 0.680, we get 2, or approximately 2.5. That is not a whole number. So what do? We now have a non-whole number. So we have 7, 9, 1, and 2.5 as our ratios. But if we take all of them and multiply them by 2, doop, 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 we can go from 2.5 to a 5, so a whole number, which is what we need, and then 2, 18, and 14. So if you come across a problem and you get a fraction, if you get 1.3, you'll multiply by 3. If you get 2.5, you'll multiply by 2 in order to get to your first whole number that you can get to. So just keep that in mind. If you see those, if you see fractions, if you do not see whole numbers, you know that you have to manipulate all of your numbers. So it's 7 to 9 to 1 to 2.5, or 14 to 18 to 2 to 5. Now that we have this, we have our empirical formula. C14, H18, N2O5. That is very large. So now we need to take our empirical formula and convert that into a mass per mole. So take our 14 times by 12.011 gives us 168.154 plus 18.144 plus 28.014 plus 79.995. So we add all these together, and all I did was I took 14 times by 12.001, 18 times by 1.008, 2 times by 14.070, 1.007, and 5 times by 15.999 to give me my empirical formula's molar mass. Then I add all these together. And I get a value of 294.31 grams per mole, which tells me that my empirical formula and my molecular formula are the same. So this is the empirical formula and the molecular formula. Our molecular formula and our empirical formula for NutraSweet. Okay, if those values are not the same, then you're going to take the molar mass, your molecular mass, divide it by your empirical formula mass to get a number. That number is basically what you'll multiply your empirical formula by to get to your molecular formula. So let's see what happens when we do this one. So we've got caffeine. By mass, we have 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and 16.5% oxygen. Sorry. So we're going to convert each of these into moles. So we're going to take our 49.5 grams of carbon, 5.15 grams of hydrogen, 28.9 grams of nitrogen, and 16.5 grams of oxygen. So you guys know what I'm doing already. We've done this like 3 times already. I'm just converting from grams of each into moles of each. So I get 4.12 moles of carbon. When I take my hydrogen, go from grams into moles. I take my 5.15 divided by 1.008. We get 5.11 moles of hydrogen. And then for our nitrogen, 14.008, sorry, 007 grams. So 28.9 divided by 14.007, 2.06 moles of nitrogen. As a note, this is not where we round. We do not want to round until the end when we're figuring out our numbers. We want to keep all of our significant figures here so that when we divide everything out, we get more reasonable numbers. If you round a lot, when you do this step up here, the step I have in red, a lot of times that will mess up if you've done a lot of rounding. So try not to round, try not to overly round with these. Okay. Until the end, at which point you will round to a number. Okay. Now I've got my moles. My oxygen is my lowest, so we're going to divide by 1.03. And I get approximately 4, approximately 5, approximately 2, and 1. So my empirical formula is C4, H5, N2O. Let's figure out what the molar mass of that is. So 4 times by 12.011 gives us 48.044. 5 times by 1.008 gives us 5.04. 2 times by 14.007 gives us 28.014. And then 15.999 for 9999 for our oxygen. Add that all together. We get a value of 97.097 grams per mole for this empirical formula, which is not the same as our molecular formula or molar mass. So we need to take our molar mass divided by our empirical formula's mass to get us a number that we need to multiply our empirical formula by. So we're going to take 195 grams per mole divided by 97.097 grams per mole, giving us 2.00, so approximately 2. So we're basically going to take this empirical formula, multiply it by 2. So C4H5 and 2O. We're going to multiply this by 2, giving us C8H10N4O2 as our molecular formula. So this is our empirical formula, the C4H5 and 2O. Our molecular formula is C8H10N4O2. Voila. Okay, let's try some combustion analysis. So we can use combustion analysis, so taking and performing a combustion reaction in order to determine our empirical formula. You cannot use this to get your molecular formula. You have to have a molar mass in order to get a molecular formula, but we can get our empirical formula using this information. So we've got, remember combustion analysis, we've just got some hydrocarbon. Sometimes that hydrocarbon will have oxygen or nitrogen or sulfur in it as well. Doesn't really matter as long as it has carbons and hydrogens. We add that into some amount of oxygen gas that combusts to produce carbon dioxide gas and water vapor. And these coefficients, these stoichiometric coefficients, are going to be based on your formula for your compound. So with this, we don't actually need to know what our formula is because we're basically going to go from grams of our substances into moles of our substances into moles of our element, which will tell us the moles of the elements here. So let's start out. So toluene is composed of carbon and hydrogen, and when we burn it, we yield 5.86 milligrams of carbon dioxide and 1.37 milligrams of water. Let's find out what our empirical formula is. So we have 5.86 milligrams of carbon dioxide. We can just convert that into grams of carbon dioxide. It doesn't really matter because as long as we do the same thing to each one, we will stay consistent and we'll still get the same numbers. But here we go. So we've got 5.86 grams of carbon dioxide and 1 mole of carbon dioxide has a molar mass of 44.009 grams. So we're going to take our 5.86 divided by 44.009, giving us 0.133 moles of carbon dioxide. And then we can go from moles of carbon dioxide into moles of carbon. 1 mole of carbon dioxide only has 1 atom per unit, so that would give us 1 mole of carbon, giving us a total of 0.133 moles of carbon. Same thing with our water. Basically convert it from milligrams into grams. And 1 mole of water has a molar mass of 18.015 grams. So we take our 1.37 divided by our 18.015, giving us 0.0760 moles of water. And then for every 1 mole of water, there's 2 hydrogens. So we produce 2 moles of hydrogen, giving us 0.152 moles of hydrogen. Our moles of carbon are smaller, which makes sense. So we're going to divide each by 0.133. And we get 1 here. And we get 1.14 here. So 143. What do we need to do in order to get this to a whole number? This can be trial and error. You can take and you can continue multiplying this out until you get a number that is a whole number. I'm going to tell you now the number is going to be, what is it, 6? Yeah, no, sorry, 7. So you can go through, you can multiply it out and find out, but this should be a 7. And when we do this, we get a value of 7 here and a value of 8 here. So this is a tricky one, but you basically just keep multiplying it out. If you have fraction form on, it might help, but probably not really. So what do I do if I didn't already know? I would take the 1.143 multiplied by 2. That gave me 2.286. That's not right, so I divide by 2. Then I multiply by 3. That gives me 3.42. That's not correct, so I divide by 3. I'd multiply by 4, giving me 4.572. That's getting close. I would divide by 4 again, and then multiply by 5, giving me 5.715. Multiply by 6, giving me 6.858. And then finally multiplying by 7 to give me 8.001. So I know that that is a correct number. So my empirical formula here is C7H8. So this is a little bit trickier. But if you see something like this, just keep trying numbers that you can multiply by in order to get to a whole number. And don't be discouraged. Let's try this last problem. We've got 0.1005 grams of menthol, which is composed of carbon, hydrogen, and oxygen. And when it's combusted, it produces 0.28929 grams of carbon dioxide and 0.1159 grams of water. And we want to know what it's supposed to be menthol's empirical formula is. So let's look at menthol. Okay, so we're going to go from grams of carbon dioxide into moles of carbon dioxide into moles of carbon, grams of hydrogen, or grams of water into moles of water into moles of hydrogen. And we are going to have an additional step from the last one because we now have oxygen in here. So you may have noticed the last one did not have a mass of our starting material. That's because we need this information in order to go from our grams of our sample into grams of oxygen. So once we get into moles of carbon and moles of hydrogen, we now need to go into grams of each of those substances, and then we can subtract it from our mass of our sample. So we have 0.2829 grams of carbon dioxide. So the first steps are going to be exactly the same. There are a couple of additional steps that we will have in here, and I will highlight those. So we're going to go from grams of carbon dioxide into moles of carbon dioxide. So taking our 0.2829 divided by 44.009, giving us 0.00648 moles of carbon dioxide. And then for every 1 mole of carbon dioxide, we produce 1 mole of carbon, giving us 0.006428 moles of carbon. The additional step we're going to do here is we're going to go from moles of carbon into grams of carbon. So 1 mole of carbon is going to have a mass of 12.011 grams, giving us 0.07721 grams of carbon. Then we're going to take our water, 0.1159 grams of water. 1 mole of water has a mass of 18.015 grams. Giving me 0.006434 moles of water. And then for every 1 mole of water, we produce 2 moles of hydrogen atoms, giving us 0.01287 moles of hydrogen. And then we're going to do the same step where we go from moles of hydrogen into grams of hydrogen. So 1 mole of hydrogen atoms has a mass of 1.008 grams, giving us a total of 0.01297 grams of hydrogen. Now that we have our grams of each species, we are going to be able to subtract it from our grams of our sample to get our grams of our oxygen. So we have 0.1005 grams of menthol. And we subtract 0.07721 grams of carbon and 0.01297 grams of hydrogen to give me 0.0103 grams of oxygen. And then we can take that gram amount and convert that into moles. So 1 mole of oxygen has a mass of 15.999 grams, giving us 0.000645 moles of oxygen, which is our smallest number by a lot. So we're going to take that and divide everything out by 0.000645, 0.000645, 0.000645, and what we get is a 10 here, or approximately a 10. We get approximately a 20 here, and we get equals a 1 here. So our empirical formula for menthol is C10H20O. So that is our menthol empirical formula. That is everything for today. Have a great day and a great week. Bye, guys.